Have you ever wondered how a company figures out how to maximize its profit with a limited budget? Or how engineers design the strongest possible bridge using the least amount of material? Well, they're all solving the same kind of puzzle. How do you get the best possible result when you have to follow certain rules? Today, we're going to unlock the mathematical key to that puzzle. It's called Lagrange Multipliers. Sounds a little intimidating, I know, but trust me, it's an incredibly elegant idea. Let's dive in. So, to get our heads around this, let's start with a really simple question. Imagine you're hiking on a mountain. You want to get to the highest altitude you possibly can, but you can't just wander anywhere you want. You have to stay on a specific trail. So how do you find that peak point along your path? This right here, this is the exact problem that Lagrange multipliers were made to solve. Here's our game plan for today, our path up this mountain of a topic. First, we're going to discover the simple, beautiful idea at the very core of it all, the why. Then, we'll map out the step-by-step process to actually get an answer. That's the how. And finally, I'm going to share some crucial pro tips, some shortcuts that'll make your journey way, way smoother. Okay, so let's get back to our mountain. In math, we'd call the mountain's surface our objective function. We'll call it f of xy. It's just the thing we want to maximize, our altitude. The trail that we have to stick to, that's our constraint, and we'll call that g of xy. The whole secret to solving this thing lies in understanding just two key visual ideas. First up, level curves. You might know them as contour lines. If you've ever looked at a topographical map, you know exactly what I'm talking about. Every single point on one of these lines is at the exact same altitude. If the lines are packed really close together, that means the mountain is super steep right there. The second idea is something called the gradient vector. The easiest way to picture it is as a little arrow at any point on the mountain that always points in the direction of the steepest climb. It's a compass that always points straight uphill. And here's the critical connection. That steepest uphill arrow is always perfectly perpendicular to the flat contour line at that exact same spot. And here it is. This is the big aha moment. Think about it. If you're standing at the absolute highest point you can possibly reach on your trail, you're not going up anymore, and you haven't started going down yet. For that one brief moment, your path has to be perfectly level, right? And what does that mean? It means your path must be running exactly parallel to the mountain's contour line at that point. They just kiss each other. They're tangent. Okay, so how do we take that really cool geometric idea and turn it into math? Well, it's actually pretty simple. If the path and the contour line are tangent, it means their perpendicular vectors, their gradients, have to be pointing in the exact same direction, or maybe the exact opposite direction. One might be longer than the other, but the key is they're parallel. We capture that whole relationship with this one beautiful equation. The gradient of f equals some number, lambda, times the gradient of g. This is the heart of the whole method. Okay, so that's the why. It's this awesome geometric idea. But how do we actually use it to find an answer? Let's take that idea and turn it into a simple three-step recipe that turns our picture into a set of equations we can actually solve. We'll call it our three-step recipe. It's super straightforward. First, step A, we set up our system of equations using that core gradient idea. Second, step B, we roll up our sleeves and do the algebra to solve that system and find our candidate points, the potential spots for our max or min. And finally, step C, we test those points to see which one's the winner. Step A is all about setting up the system. That main vector equation we saw, it actually breaks down into a few pieces. We make one equation for the x component and one for the y component. We do this using what are called partial derivatives, which is just a fancy way of saying, look at the slope in only the x direction, then only the y direction. So the x slope of the mountain equals lambda times the x slope of the path. Same thing for y. Then you just add in your original constraint equation and boom, you have a system of three equations for your three unknowns, x, y, and lambda. Now we get to step B, which, let's be honest, is usually the trickiest bit, the algebra. The whole goal here is to get rid of lambda and find a relationship between x and y. A really common tactic is to solve for lambda in each of the first two equations and then just set them equal to each other. Once you get a simple relationship, something like, say, x equals 2y, you can plug that into your third equation, the constraint, to solve for the actual numbers, the coordinates for your candidate points. And finally, step C is the easy part, the final check. The algebra in step B might have given you a few possible spots for a peak or a valley. So how do you know which is which? You just plug the coordinates of each of those candidate points back into your original function, f of xy, the one for the mountain's altitude. The point that gives you the biggest number? That's your maximum. The smallest number? That's your minimum. Simple as that. All right, you've officially got the core recipe down. But before we wrap up, let's go over a few pro tips that will save you a ton of headaches and help you avoid the common mistakes when you're actually out there solving these things. First thing, and this is probably the most important, remember lambda, the Lagrange multiplier itself? Don't waste your time solving for its final numerical value unless a problem specifically asks for it. Lambda is just a tool, like a temporary scaffold we use to find the relationship between x and y. Once it's done its job, you can pretty much just forget about it.
Now, here is a fantastic shortcut. Let's say you're asked to minimize something complicated, like the distance formula with that annoying square root in it. Well, a lot of the time, you can optimize a much simpler version instead. For instance, minimizing the distance is the exact same thing as minimizing the distance squared. The location of that minimum point won't change at all, but the math, the derivatives, will be 1,000 times easier to deal with.
Just two quick little warnings. First, this method works best when your path is a closed loop, like a circle or an ellipse. If it's just a line segment, you also have to remember to check the endpoints. Second, sometimes the math can miss weird spots, like sharp corners on your path. So it's always a good idea to just check those oddball points manually, just in case. So we've figured out how to find the highest point on a mountain when we're stuck on a single path. But what if you had to follow two rules at the same time? Like, say, finding the hottest point on the surface of the Earth, but you can only look at the intersection of the equator and the prime meridian. The great news is the idea scales up perfectly. You just add a second multiplier, we usually call it mu, and a second gradient term to the equation. So that's really the heart of it all. Lagrange multipliers aren't just some random formula to memorize. They are the mathematical expression of a simple, powerful geometric truth. At the best possible point, your direction of travel is momentarily parallel to the landscape. Once you really see that picture, the algebra just becomes a tool, not a chore. So the next time you see a complex system with limits, whether it's an economy or a neural network, you can ask yourself, where are the gradients lining up? Thanks for joining me.